Ever wondered how transactions in database systems maintain data integrity? Let's delve into it. In the realm of databases, transactions play a pivotal role in maintaining the integrity of data. They encapsulate multiple database operations into a single unit of work, ensuring that all operations either succeed together or fail together. This prevents data inconsistencies and preserves the reliability of your database, especially in environments with multiple concurrent users or applications accessing the database simultaneously. The behavior of transactions is governed by the ACID properties: atomicity, consistency, isolation, durability. These properties ensure data reliability and consistency in the face of potential anomalies or errors. In essence, transactions are the sentinels of your database, safeguarding the integrity of your data. Now that we understand what transactions are, let's explore how to create a transaction in a database system. To start a transaction, we use the begin transaction or start transaction statement. In the world of database systems, transactions are akin to a symphony, each note, each instrument playing its part to create a harmonious whole. And just like a symphony, our transaction begins with a cue, a signal to all the players that the performance is about to start. This cue comes in the form of the begin transaction or start transaction statement. Imagine you're a conductor, ready to guide your orchestra through a complex piece. Your baton is this begin transaction statement. It's an announcement to the database that you're about to perform a series of operations that need to be treated as a single unit of work. It's a powerful tool, one that offers you control and coordination over the actions that are about to transpire. Let's take a look at an example. If we were to begin a transaction, we would simply write the command begin transaction in our SQL interface. Just like that, the curtain rises and our transaction performance begins. The begin transaction statement is the first step in our journey through the world of database transactions. It's the foundation upon which we build the rest of our operations. It's an invitation to the database system, a request for it to patiently wait for our next series of commands. The beauty of this statement lies in its simplicity. It doesn't need any parameters. It doesn't ask for any additional information. It's a straightforward, unequivocal declaration of intent. We're starting a transaction and we want the database to prepare for the actions that are about to follow. But it's not just about the start. The begin transaction statement also signifies a commitment. It's a promise that we will either execute all the subsequent operations successfully, or we won't execute them at all. It's our pledge to maintain the integrity and consistency of our data. With our transaction successfully initiated, it's time to execute some SQL statements. Within our transaction block, we can now perform various database operations. This is where the real magic happens. To bring this concept to life, let's consider a few examples. First up, we have the update statement. Imagine you're running a bank and need to decrease the balance of an account by 100 units. You'd use a statement that could look something like this: update accounts, set balance, =balance, 100 where, account_ID =123. This operation modifies the data in your accounts table, specifically targeting the balance field of the account with the ID of 123. Next, let's say you need to record this transaction. You'd use the insert statement to add a new row to your transactions table. Your statement could look like this: insert into transactions, account_ID, amount, transaction_type, values, 123, 100, withdrawal. This operation adds a new row to the transactions table, recording the account ID, the amount, and the type of transaction. But what about if you need to retrieve data? That's where the select statement comes in. A typical select statement might look like this: select asterisk from transactions where account_ID =123. This operation retrieves all transactions that were made by the account with the ID of 123. And finally, when we need to remove data, we have the delete statement. For instance, delete from transactions where transaction_ID =999. This operation removes the row with the transaction ID of 999 from the transactions table. Each of these operations, update, insert, select, and delete, are part of our transaction. They're all encapsulated within our transaction block, and they're all governed by the principles of atomicity, consistency, isolation, and durability. This ensures that our data remains reliable and consistent, no matter what happens. Now, let's discuss what happens when we want to make all these changes permanent. If all our operations are successful, we can commit the transaction. Let's dive into the commit statement, an integral part of our transactional journey. Once we've executed all our SQL statements within the transaction block and are satisfied with the changes, we use this statement to make all the modifications permanent. Think of it as the final seal of approval on our transaction. Imagine you're relocating your office and you've packed all the items into boxes. The commit statement is like taping up those boxes, an affirmation that everything inside is ready for the move. The syntax is straightforward. You simply write commit and execute it. Just like this. Commit. Once you hit commit, all the changes you made during the transaction are saved to the database. These changes are now visible to other users and transactions. The database is updated, and the transaction is complete. Let's look at an example. Suppose we have a banking application where a user is transferring $100 from their account to another user's account. We begin the transaction, debit the amount from the sender's account, and credit it to the receiver's account. If all these steps are successful, we're ready to commit the transaction. So we say, commit. And just like that, the transfer is complete. The $100 has moved from one account to another, and the database records reflect this change permanently. The commit statement is our green light. It's the point of no return. Once it's executed, we can't undo the changes made during that transaction. It's like sending off the moving truck with the taped-up boxes. There's no unpacking now. The changes are here to stay. But remember, the commit statement is only used when everything within the transaction has executed successfully. It's your stamp of approval, your final say in the matter. But what if something goes wrong during our transaction? Let's explore that next. Sometimes things don't go as planned. In such cases, we can roll back the transaction. Let's delve into this a bit more. In the world of database transactions, not everything is always smooth sailing. Errors may occur, or perhaps you may simply change your mind about certain modifications. That's where the rollback statement comes into play. The rollback statement is like our very own time machine. It allows us to undo the changes made since the transaction began. To put it simply, it's our safety net, our plan B when things go awry. Imagine you're working on an intricate painting. You've spent hours perfecting each detail. Suddenly you spill a cup of coffee over a section of your masterpiece. If only you could rewind time and undo that mistake. Well, in database transactions you can. Let's look at an example. Suppose you're updating an account balance and inserting a record into the transactions table, just like we did in the previous scenes. But then, an error occurs. Maybe you input an incorrect account ID, or perhaps the balance doesn't adjust correctly. In SQL, you'd execute the rollback statement. It's as simple as typing rollback and hitting enter. Once you do that, the database system reverts to the state it was in before the transaction began. The account balance and the transactions table return to their original state, as if nothing happened. It's important to understand that the rollback statement cancels the entire transaction. It's an all-or-nothing approach. If you've executed multiple SQL statements within a transaction, a rollback undoes all of them, not just the last one. The beauty of the rollback statement lies in its power to preserve data integrity. If something goes wrong, it doesn't leave your database in a state of disarray. Instead, it ensures that your data remains consistent and reliable regardless of any bumps along the way. Finally, let's discuss how we can control the interaction of our transaction with others. We can set the isolation level for our transaction to control its interaction with concurrent transactions. Now, let's delve into an optional but crucial part of transaction management, setting the transaction isolation level. This is done using the set transaction isolation level statement. You might be wondering, what are isolation levels and why do they matter? Well, they define how one transaction interacts with others running at the same time. Take a look at this example. Here, we're setting the isolation level to serializable. Set transaction isolation level serializable. This level ensures that our transactions are executed in a serializable manner, meaning they don't interfere with concurrent transactions. Besides serializable, other common isolation levels include read committed and repeatable read. Each level offers a different balance between data consistency and transaction performance. Choosing the right isolation level for your transaction can significantly influence the reliability and efficiency of your database operations. And that's how we create and manage transactions in a database system. Remember, transactions are key to maintaining data integrity and consistency in your database.